Hi, this is Professor David Farina. In today's video, we're going to be discussing Jovian moons, rings, and Plutoids, specifically the moons of Saturn. Let's get started. So, the large moons of Saturn are visible from Earth, and one of them that's probably the most interesting moon in the Saturnian system, and possibly one of the most interesting moons in the entire solar system, is the moon Titan. Now, the reason Titan is such an interesting moon has to do with its atmosphere. Titan has some very interesting chemistry. It is a very organic, rich world. And by organic, I mean carbon compounds. And in table 23.3 here, you can see all of the different carbon compounds that Titan has in its atmosphere. And I'll take a moment here to let you look over those. Just pause the video. So now that you've looked over the table, you'll notice that many of these different chemical compounds are things that you might be familiar with. Many of them are fuels. And by fuels, I mean like combustible materials that you, for instance, propane you use on a grill. And these fuels are oftentimes associated with things that used to be living. And so the thought is that these materials, these organic materials, could be an indicator that life is possible on Titan. Now, to be clear, we're not talking about life that's like you and I. We're talking about methanogenic life forms, methane-eating bacteria. So methanogens are found here on Earth, and if methanogens can live here, we think maybe they could live on Titan. So that's one of the main things Titan is kind of famous for, is for the potential for life. Now, in terms of size, Titan is actually pretty big. It's about the same size as Jupiter's moon Ganymede, which is significantly larger than our Earth's moon. It's got a rocky core and has a large amount of ice on its surface, a thick atmosphere, and we've actually launched a spacecraft to here, which we'll talk about in a moment. So we were able to get this image from the Cassini spacecraft, and the Huygens probe landed on the surface of Titan in 2005. Now, when we landed, we were able to measure some of its atmospheric compounds, and we realized that it's mostly nitrogen with some methane and ethane in its composition. The surface pressure is actually pretty high. It's 50% greater than the air pressure on Earth. Its temperature is pretty cold, 94 Kelvin, which is negative 290 degrees Fahrenheit. And an interesting process actually occurs here that's similar to Earth's water cycle. But instead of water, its methane and ethane are able to condense, and actually rain of methane and ethane can fall from clouds onto the surface of Titan, and we actually can get pools or lakes and rivers and streams of this methane on the surface of Titan itself, which is really, really amazing. So it has this water-like cycle, but with methane. This means that methane must be constantly being replenished. There's some sort of breakdown of ammonia, we think, to cause this. So before the Huygens probe, we could only look at the surface of Titan through infrared to look through the clouds. But once we got past the clouds, Huygens probe revealed very bright and dark regions of the surface. The bright regions are probably methane or ethane ice, and there are rocks essentially on the surface of Titan that are actually water ice that's frozen. So the rocky terrain is actually water ice. Think about that for a second. Rocks made of water ice. You might not think of ice as a rock, it's actually a mineral. So a mineral has 5 main components that allow it to be classified as a mineral. It has to be naturally occurring, it has to be inorganic, it has to be a solid, it has to have a definite chemical composition, and it has to have an orderly arrangement of atoms. Water ice fits all of these criteria. So in fact, it is a mineral. Now, Huygens discovered outflow channels and possibly liquid methane pools, as I've already discussed, and here are some of those images. It looks much like the rivers and streams of Earth. Saturn also has a number of smaller moons as well. So here's Titan for scale compared to the Earth's moon. And then we've got Enceladus, Dione, Iapetus, Phoebe, Mimas, Tethys, Rhea, and Hyperion. So these are all of the moons of Saturn that are of interest. There are many, many more. Hyperion is interesting in that it does not have enough gravity to pull itself into a circular or a spherical shape. So gravity is the main way that these worlds become spherical, and it's just too small. So, like the moons of Jupiter, Saturn's moons are formed of ice and rock. Many of them are heavily cratered surfaces that are geologically dead. On Iapetus, the leading side of the planet, or the moon, is darker than the rest of the surface because of some dark deposits on it. So you can see that in this image. We've got a darker surface here and a brighter surface. And a big, big crater here on the edge. Here's Phoebe and Tethys. And Phoebe is small, dark, and cratered. Look at this thing. It's got all sorts of pockmarks all over it. Same thing here with Tethys. Tethys being slightly more active in terms of geologic activity. You can see some cracks in its surface as well here. Enceladus has some of these really cool blue tiger stripes across its surface, indicating quite a bit of activity is going on here. A very bright, very crater-free surface at some locations, with cracks and crevices and folds and faults all over it. And when we look at Enceladus from a spacecraft image, we are actually able to see that it has icy particles venting from its south polar region, which is kind of interesting and plays a role in the formation of rings around Saturn. Now, moons can be co-orbital, and what that means is that some of these moons are able to exchange orbits, and so we have this little sequence of events here. We start off with the bigger moon at the higher orbit here, the smaller moon at the lower orbit. The gravity of the bigger moon pulls the smaller moon faster and faster and faster. When you gain speed, you increase the altitude of your orbit. So the little moon is kind of now in line with the bigger moon, and the bigger moon is dropped down because it's losing speed due to its gravitational interaction. It slows down to now the lower orbit, and the little moon is on top. And this sequence then goes back in reverse, and they switch off again. So kind of an interesting sequence of events here where we have co-orbital moons. Once again, we have Titan here. So the thick atmosphere of Titan, some additional images for you. There's a cool picture of there's Titan and its atmosphere. So there's another image of Titan. Some pictures from the Huygens probe that landed on Titan. You can actually see some of the topography that we were talking about earlier. Some of those drainage channels. and that icy surface with the rock that is actually water ice. Looking at the atmosphere of Titan, you can see that it has many layers. We've got an ultraviolet absorbing haze over the very top, an ultraviolet and optical invisible light haze layer, a main haze layer, an aerosol haze, methane clouds with methane rain coming out of them, and finally you reach the surface. Notice that temperature and pressure changes as we go up through the atmosphere in interesting ways. Many of these charts look much like the ones you would see for Earth's atmosphere as an interesting analogy. Thanks again for watching today's video on Jovian moons, rings, and Plutoids, specifically the large moons of Saturn. Thanks for watching, and I hope you have a great rest of your day. If you like this video, please click that like button. If you would like to learn more, please click subscribe. And if you'd like to get a notification each time I make a video, please click the little bell at the bottom. Thanks again. Have a great rest of your day.